So, hey, good evening, everyone. I am Rohit Mandal, and today I am going to present to you one of the most important topics of all times. It is on something which actually influences us all in our day-to-day life. It is something which keeps us warm. It is something which actually causes days and nights, and actually is responsible for providing us the life and maintaining the life on our planet Earth. So, probably you guessed it right. Yeah, you guessed it right. It's about the sun. So let's begin and let's explore the sun. Now, we all know that our solar system is a system of the sun and the objects that orbit it under the influence of something we term as the gravitational force. Now, we know that there are many objects, many bodies in our solar system which orbit the sun. The sun, we can say, is a central object of the solar system, and the other larger objects or smaller objects, like we have planets. There are a total of 8 planets in our solar system, of which we have 4 terrestrial planets, that is, the Mercury, Venus, our own Earth, and Mars. We also have the 4 gas and icy giants, which are the Jupiter, the Saturn, the Uranus, and Neptune. Along with this, there might be a question that why these 4 planets, these giant planets, which are bigger than our Earth, or even like the Jupiter, Saturn, Uranus, and Neptune, are not terrestrial planets. And what does it mean to have a gas giant or an icy giant? Now, let me make it clear that probably you might all know, but still let me make it clear that Jupiter doesn't have a surface, a solid surface. It does have a solid core, a solid probably iron core, but it doesn't have a surface in it. It's just made up of gases, tons and tons of gases into it. And is similarly the case with the other planets too, which has a solid core but lacks solid surface. If, in short, the sun actually bounds all the members of its solar system with its gravitational force of attraction and helps maintaining a stable system which we all can see and actually appreciate. Now, there are not just planets, there are also asteroids, numerous asteroids, which are like the famous asteroid belt between the planets Mars and Jupiter, which have asteroids of all different sizes and shapes. And they also orbit the sun, like the planet Earth and the other planets. There are also a couple of dwarf planets like Ceres, Makemake, and also some other, which also does the same. So it is what engulfs the solar system. The solar system, you might say, may end till this, but no, it's not that. The solar system exists and actually extends to far beyond what you can even think. It is known as the heliosphere. Probably we won't go into much details of the heliosphere here, but we will surely discuss towards the end too. So let's move on. Now, how about comparing the sun from different worlds? Let's compare the sun, the view of the sun, as it would be if you were on the surface of Mars, and comparing it with what we see in the present day from the Earth. Now, let's discuss about it. Somehow, suppose you are on the moon, you move to you move to the Mars, and someday for real you move there, and you are able to watch the rising and setting of the sun. Now, one thing I can assure you that you will truly appreciate the beauty of this event, but will also notice a considerable difference compared to that of the Earth. But you would observe that this rising and the, as you can see in case every day, that in case of rising and setting of the sun on Earth, it would be kind of an orange yellow background of the sky that you will ever see. Every day it would be like that. But on Mars, it won't be like that of an orange or yellow background. Like you can see in the bottom left image, that this is from the surface of Mars and it's a real image. Sorry for the quality maybe, but it's actually the sun you can see there on the white as sun, and it has, you can see the blue sky there. So you might ask, of course, the question that what makes the sky there at the rising and setting to be blue, and what makes in our at our Earth as the it is around orange or yellow. So it is actually due to the atmospheric content. Now the atmospheric content of our atmosphere of our Earth and of our Mars is quite different. Our atmosphere consists of oxygen, nitrogen, and some other trace gases too. But for Mars, it is not so. It doesn't contain so much of oxygen or nitrogen. It also has a thin atmosphere compared to Earth. Moreover, the thing is that the dispersion and the scattering of light that takes place, that for the sun rays that emit from the sun and reach the atmosphere of these two planets and then scatter together, actually combinedly causes the sky of those individual planets to appear in this way. Even if you visit the other planets someday, you will even notice some other considerable differences. You might notice a combination of some other colors too. So it is about the sun, which can be viewed from different worlds, but at least you can assure that you will actually see everything differently, but the same event. Also, you might even argue that are there any clouds on Mars? Because you can even see like clouds on our planet, right? But on Mars, it is not so. There are rarely some clouds, but that is also some seasonal occurrences of clouds are there. On Mars, you will find clouds to be around the equatorial region, that also in some weather conditions. And these clouds, as you might think, doesn't contain liquid oxygen, liquid water. It actually is a combination of some icy crystals and water ice, but not liquid water. So the clouds on Mars, if you even see, which is actually a rare event, will consist of solid form of H2O. So let's move on. Now, there is one basic and a very fundamental question. Now, is the sun the only star in our solar system? The answer is of course yes. The sun is the only star in our solar system. But there is another question too, that why is the sun even called a star? Or even you may go further to ask that what qualifies sun as a star, or what are stars exactly? And does sun qualify all of the properties what a star should? So the answer is of course yes. So what is a star? Stars are objects in the universe which are capable of producing self-energy through fusion reaction of gases. They are burning balls of gases producing luminescence, or you can say brightness. Now, luminescence and brightness, you can say equivalent to each other, but not exactly same. But we will not get into that. Also, you can take reference from the web for searching more about fusion reaction if you're interested in that. There is a link in that. And also you can see the fusion reaction of hydrogen here in the given picture, which is forming the helium nucleus. Now, these are the properties a star should have. Now, our sun is actually the only star of our solar system, because it is the only object in our solar system which satisfies all of these criteria. It is actually a star because it is capable of producing self-energy through the fusion reaction of hydrogen nuclei, turning them into helium nuclei. That is why it is a star, the only star in our solar system. Now let's move on to something interesting and something hypothetical. Now, can you imagine the Earth without the sun, or even the solar system without the sun? I know it's probably not possible, but the thing is that there is no harm in visualizing, right? So in the left side image, you can see there is a normal scenario. We have the sun, we have the earth and the other objects in the solar system too. But somehow you are able to just make the sun disappear. Now, by the term disappear, I don't mean that you make the sun invisible somehow. I just mean that you somehow, with some superpower, that you turn the earth, that you make the sun go away, make it out of existence somehow. Then what would be the effects of it on the solar system? Also, maybe we can just consolidate our view only on this earth. So can we all visualize what can be the effects of it? Now, there are many effects that it would be because of this event, this massive event. But let's just point out some of these things. Now, we all know that plants require sunlight for photosynthesis, right? So if the sun is even not there, so the photosynthesis will eventually stop, which will cause the life to be almost impossible to sustain. Now, this is one of the most important criteria that you would actually observe on the Earth if you are there in this kind of an event, which is kind of terrible to think about even. Now, the other things is that the atmosphere of our Earth, as you all might know from your geography classes too, is that the heat that our atmosphere traps is the heat from the sun, the source of the heat. The source of the heat is actually the sun, and that heat enters our atmosphere, then reaches our surface, reflects back, and most of it is, and half of it is actually like absorbed in our atmosphere. But if the source of heat is not even there, like the sun is made to disappear, and go out of existence, then the source of heat would not be there, and the Earth would eventually become an icy and cold place to live. The Earth will not be just a planet, it would be like covered in entire ice. The whole oceans will freeze, and it would be just like some hail planet, just like everywhere it will be frozen and unsuitable for living. Also, one other phenomenon that would occur is that as the sun was there, there was a gravitational pull attraction, which for which the Earth was and the other planets were also bounded by their gravitational forces towards the sun in their particular fixed orbits. But as the sun is not there, it will actually eventually move out into the outer reaches of this solar system in the universe. Now, the chances of the Earth colliding with the other planets in our solar system is actually slim, right? Because it's just a pale blue dot, as you might know already. It's just something in the entire universe which just even visible from a large distance. So the chances, if you ask that it actually collide with any other planet like Jupiter or Saturn, yeah, there are chances, but it's very slim that it would. But what we can assure is that the Earth will eventually move out of the orbit. So let's move on. So this is a very fundamental question, but yeah, I know that some of you will be get shocked because even I came to know about this fact that the sun's color is actually not yellow or orange. I came to know very late about it, probably in class 7th or 8th, or maybe even further. But it's like I had the same reaction, and I hope that I believe that some of you will all actually have the same reaction as this man in this picture. Because yeah, this is a fact, and you should know that the sun is actually not yellow or orange in color. It's actually white in color. What you can see here is the picture of this photosphere of the sun, and on it are some sunspots too. We will discuss about them all in details. So let's move on. Now let's talk about some general information about the sun. Now, how big is the sun? You might always have read about that the sun is very huge. It is enormous in respect to the Earth. But can I give actually to you a very important comparison to it? So let's compare. Now, the radius of the Earth is around 12,750 kilometers approximately. But the radius of our sun is around 6,96,000 kilometers, which is a huge difference, right? Now, if you calculate the distance of the diameter by the diameter of the Earth, diameter of the Sun divided by the diameter of the Earth, you will get that there are almost 109 Earths on that can fit across the diameter that you can see here, right? Probably you can see the pointer that there are around 109 Earths that can fit across the diameter of the Sun. Now, coming to the other infos too, the mass of the Sun is around 2 into 10 power of 30 kilograms. That is 2 followed by 30 zeros, right? It's enormously heavy. Now, there are some other factors like the density is around 146 gram per centimeter cube. Now, you might ask, what does it actually mean? So let me give you a quick visualization and let's do some assignment kind of a math and make it more interactive, right? So what does it mean that it has a diameter of around these many, like 146 gram per centimeter cube? Now, what is centimeter cube? Now, if you imagine dice, right, in Ludo or something, you actually play with dices, right? So the dice eventually has around the size of 1 centimeter, right? It's actually a cube of 1 centimeter. Now, the volume thus of the cube would be around 1 centimeter cube. Now, now let's imagine that the sun is actually made up of innumerable number of blocks of innumerable number of dices of 1 centimeter cube volume. So can you say that how many such number of cubes will be required to fill up the entire sun? I actually give you this assignment. Can anyone say that how many number of uh, cubes would be actually necessary to actually fill up this entire sun? Can anyone calculate? Probably I will also calculate too. It's actually pretty easy to calculate too. It's just like you have n into the 1 centimeter cube volume. Like 1 centimeter cube volumes, you take n number of those cubes, and that would be equal to the volume of the sun. So what you calculate is 4/3 of pi r cube, where r you can take as 6,96,000 kilometers. So let's calculate that. Remember to actually convert these kilometers to centimeters too. Probably you can just cross-verify my calculations too, because it can be wrong because of a spelling mistake. But it's around 1.4 times 10 power 33. So it's around 1 followed by 10 power 33. It's around 1 followed by 33 zeros. These many number of these dices would be required to fill up the entire sun. That sounds pretty huge, but anyways, that's the truth. You can even calculate it to be number of spheres or something. But if you have the sun filled up with just these Ludo cubes, the dices, then it would be these many number of dices. So let's talk about the surface temperature and the other factors. Now the surface temperature of our sun is around 5800 Kelvin, which is not very much, or you can have an idea of it's around like 50 degrees Celsius and you start sweating, not even 50, like 40 degrees Celsius and you start sweating. But the surface temperature of the sun is around 5800 Kelvin, right? Now the gravity of the sun is around the G value is around 274 meters per second square. Now the G value at the surface of the earth is around 9.81 meters per second square. Whereas you can see that the gravity at the surface of the sun is around 274 meters per second square. So approximately you can say that it's around the gravity of the sun is around 27 times more than that of the sun. So if you weight around 50 kilograms here, then you will weight around 1350 kilograms there at the surface of the sun if you can stand, but yeah, don't try. Anyways, so moving on, at the uh, age of the sun, it's around the same age of the solar system, because we know this that the solar system was just born out of the sun when some interstellar dust was forming, and there was some kind of a theory which stated that there was kind of a supernova explosion somewhere near, and those shock waves which traveled around space-time, and these shock waves collapsed the interstellar dust into the sun, and from it, from disks, protoplanetary disks, and all those actually was formed the other planets, including our Earth. So it is actually equal to the age of the solar system, which is around 4.6 billion years. Now, the distance from Earth is kind of interesting. It's around 150 million kilometers, and you can note that because it is also known as one astronomical unit or 1 AU. It is actually important to actually uh, take this into account when you are calculating heavy, deep space distances. You actually don't calculate them in kilometers because there are pretty vast distances. You actually calculate in terms of light years or astronomical units. So let's move on. So let's see some mathematical description of distance. Now, the suppose you are the observer and you are observing the sun. The sun is actually having a physical size of 2r dot, right? And so the thing is that uh, the diameter is 2r dot. Now r dot means the radius of the sun, and the d dot represents the distance of view, that is distance of earth eventually from the sun, which is taken as d dot, and the sun's radius is r dot, and the physical size, which means the diameter of the sun, is 2r dot, right? So what you see is the angular size theta dot, that is this angle that you can see here, this angle here is actually this theta dot here that you can see. This is the theta dot here, and this if you calculate, it comes out 2r dot by d dot with some approximations, of course. And if you calculate this in degrees, it would come out to be around 0.5 degrees. And coincidentally, this is also if you place the moon, our moon, instead of the sun here, then also you will actually get the same value. Approximately it's the same value, coincidentally, that it would be around 0.5 degree. So let's move on from here. Enough of mathematical descriptions. I know it's boring, but still, let's move on to something interesting. Now, what is a solar spectrum? Now, what you can see here is actually our solar spectrum of the sun. The graph is actually a plot of the intensity that we have received from the sun versus the wavelength in nanometers. Now, this solar spectrum is actually the emission spectrum, or which is actually continuous in nature. Now, why this is actually known as an emission spectrum and all, we will actually discuss that too. Now, coming to this is that uh, the bandwidth of the radiant energy and the plot, this shows the distribution as a plot of between the intensity of the radiation and the wavelength in nanometers. Now here that you see is that we all know that the sun actually doesn't emit its sunlight only in the visible range. It actually emits sunlight in the other ranges like the infrared, the ultraviolet rays, and also the other rays too, like the gamma rays or radio waves. But the sun, as you can note, is that it actually emits light in the almost 50% in the visible range, almost 50% in the infrared range, and just a minor amount in the UV range, which is actually good because UV rays are not very good for us, right? So it's good that the emission in the UV rays is not very much, that you can see here. And also we are focusing on the visible range because it is the optical wavelength, and the wavelength which is around 380 to between 380 and 780 nanometers. And this is the wavelength range in which we can see, right? And this is known as the emission spectrum because the radiation that is emitted from the sun is actually what we receive on Earth. And this radiation that we have, this radiation, actually when we go for a spectrometer or any other ways to calculate the spectrum of the sun, we actually get this kind of a plot here for the sun, because this is what shows that these are the kind of elements or the wavelengths that are emitted from the sun. And so as the radiation is emitted from the sun and not absorbed, right? It is emitted from the sun. That is the reason why we can see it. So this is known as intuitively the emission spectrum. So let's move on. Now, size comparison we can do about the sun. Now, we probably did a kind of 109 Earths that fit into this diameter of the sun. But let's compare with the other stars and also with the other planets. Now, here you can see, probably you have seen this picture before, but let's see this once more. That the Jupiter here, which is the largest planet in our solar system, even is so small in terms of the radius and diameter, in terms of the size of the sun. The Sun is around 14 lakh kilometers in diameter, whereas the Jupiter is around 1 lakh 50,000 kilometers in diameter. And the Saturn is around 1 lakh 20 to 1 lakh 25,000 kilometers in diameter. Whereas the Earth, as you can see here at the pointer, is around 12,750 kilometers in diameter. So it's pretty small in terms of the Sun in comparison to the Sun. Now let's move on to some other stars. You might think from this left side image that the sun is pretty big, but it's actually not so. So the sun can be compared to the other stars in our universe. Now the sun probably you cannot even see in this presentation, as I can point here, that is the smallest object in here in this right side image, and you can see that the sun actually is so small. Then you have the Sirius star, the brightest star in the night sky. Also, we have Arcturus, Betelgeuse, and that is a star in the Orion constellation. We also have Rigel before that, which is also a star in the Orion constellation. We also have the Pestel star, and there is KW Sagittarii 5346FA. Also, there are some other stars. Also, you can assume this big star to be something around VY Canis Majoris or UY Scuti, which has diameters of around 200 crore kilometers or more than that, where the sun has a diameter of around just 14 lakh kilometers. Just can you imagine that? It's pretty big. It's too big in comparison to the sun. And the sun is too big in comparison to the earth. So let's move on. Now, coming to green and purple color stars. Now, are they real? Like everyone might have wondered that there are so many color stars. There are not just white, yellow, and orange. There are many color stars, right? There are blue stars, like you all already saw in Rigel, and some other stars. That there are some other stars which actually are blue in color, and also our sun, which is white in color. There are Betelgeuse, which is red, orange supergiant star, so there are many colors, but are there green and purple color stars? Because if they are, then they will surely look magnificent, right? So ever wondered if they are part of reality? Now, sorry to demotivate, but don't get demotivated. But the thing is that, sorry to tell you, but they aren't not they're part of reality. Now, star colors, as depicted by this following diagram, is typically lying on the black curve that you can see. This astronomers actually have plotted this graph after actually analyzing lots and lots of stars. Now, this diagram, this conical figure that you can see in terms of rainbow color, this actually takes into account the visible radiation only. It also has, as we discussed, the infrared radiation, the UV radiation, and the other radiations too. But as we can just see, and we are talking about colors which we can perceive, we are concerning our discussion only to the visible range of radiation. So in this case, if this curve we know is actually what depicts the temperature of any star, and if the star has this kind of a temperature, then according to the position in this figure, we can say what color the star could be. Now, as you can see, they're at around 2000 to 3000 Kelvin temperature, which is kind of relatively cool than the other stars too, even cooler than the stars like our sun, which is around 5800 Kelvin. These are red stars. Then comes the orange stars, yellow stars, and all. We have the sun at around 5000 to 7000 range, which is we know that it's around having a surface and temperature of around 5800 Kelvin. But as we can see here, is that the position where the sun is placed is actually an intermixing of many different colors. It's actually an intermixing of majorly green, blue, yellow, and also some kind of pink or something. But we all know that in case of a prism, if you have white light coming towards the prism, it spreads into apart into all the colors that you can see. V, I, B, G, Y, O, R, all the 7 colors here. But also you can say in reverse that if all the colors mix together, they also form colored white. And even you don't need all the colors to form the white color. You can have some combination of RGB to actually form a white color too in various intensities. Now, if you have, so if you have, um, in this case, you can see that there is an intermixing of various colors. Now, you can probably say that at the position where the sun is located, at that complete position, there happens to be the green color star content to be more. Like if there were no intermixing here, if the colors on this curve were completely monochromatic, like monochromatic meaning single color to single color, so if there were no intermixing of different colors and with a visible range, then the sun probably could have been light blue or light green. But as there is an intermixing of so many colors, you can see it appears that the sun is actually not those colors. It's actually perfectly white in color. So it's pretty depressing, but yeah, we have to accept that it's actually white. Now coming to the purple color stars, it's also quite similar. It's actually having some temperature of more than 45,000 or more than 35,000 Kelvin. But as you can see that the purple color actually doesn't quite lie on the black curve. It's just a very small amount of these colors that actually appear to be there on that curve, right? So majorly we have the blue range here, the blue and white and all those blue color lying on this part of the curve. So the stars here probably you might expect it to be like little purple or violet colored, but actually as there is more blue content, the stars here would probably be just blue or blue-white stars. So hope it's clear. Let's move on to the sun's surface. Now, sun's surface, as we know, these pictures we all have seen, but the sun's surface is actually quite not smooth. It's actually very rough and is filled up with granules. Now, what are granules? We will discuss soon. And these granules are actually like these small troughs, crystal troughs, like kind of a structure, like a dry soil, which actually have been dried and there is no water. That kind of a soil actually looks like this, kind of like rough from here and there. It's like each of these is known as a granule. So let's discuss them in details. Now, let's talk about some different filtered images of the sun. Now, the filtered images of the sun probably does no justice to the images probably much, but the thing is that in terms of the different filtered images that you can see, the images, because we all know that the sun is actually white in color. Now, this right side image depicts the color of the sun we actually at the start of the presentation we always saw. We all saw, right? So this is actually the picture of the outer sphere. This is the a picture of the photosphere in white light, which has the sunspots too. Now we can also see the infrared range because we all know we actually just now read uh, that the sun actually emits in all of these wavelengths too. So if we have to measure or actually image the sun in the infrared ranges of what would the sun look like if we actually just take into account the infrared radiation, this is what it looks like. You can even apply different filters to even vary the colors too, because it's just color coding or kind of colors that you can have. Also in the ultraviolet region, you can also see some coronal streams that you can see here, that is probably visible in this ultraviolet range. Also, you will see some images of the sun in blue colors. Those are the sun images in the ultraviolet spectrum. Also, you have a fancy color in the radio, which is in blue and green. This is in radio, and also in X-rays, you can see the streams of the sun too, the corona streams too. So these are the sun images that you can have with a solar telescope or some solar telescope across some organizations that they use. So you can have those, and they will produce these kind of images. You can always search them on the web. They're very fastly available there. So let's stream into the structure of the sun. Now let me divide the structure of the sun into four main parts. One is the solar interior, then photosphere, then we will discuss about the chromosphere, and also then the corona. Now, this is not the corona which is hot in news from last 2 years. This is the solar corona, right? So, anyways, we all know that. So, let's dive into the take a look at the interiors of the sun. Now, let's actually image this picture quite deeply because we will explain this. We will actually know about it more in the further slides. We have the core at the inner bottom there of the star. Then we have the radiative zone, and also we have the convective zone. Then we have the photosphere. Above it we have the chromosphere. Then the corona, and also we can see the solar spheres and the sunspots too. We will surely discuss about all of them. Also note that between the radiative zone and the convective zone, there exists another slim layer which is known as the tachyoline, which is probably not here, which is actually not printed here, but it's actually known as the tachyoline, Tachocline. So let's discuss about each of these. Now, our sun is actually a giant ball of hydrogen and helium, and also lots of other heavier elements too. And this picture depicts and defines all of these terms that we just saw here in the previous slide. So the sun's core is actually the innermost core, the innermost part of the sun. The energy that actually is created by the thermonuclear reactions, creating extreme temperatures deep within the sun's core. As there occurs some thermonuclear reactions, we know there actually is an involvement of too much of heat and temperature there, and that increases the overall temperature of the sun, and leads to some extreme temperatures in millions and millions of degrees at the interiors of the sun, at the sun's core. We have the radiative zone where energy actually is made, which is actually made and generated, actually moves pretty slowly. The energy that actually passes through here, through this layer, radiative zone, is actually 1 by 50 crore of a part that is actually flowing through it. Like if you have like 100 units of radiation coming in, then you will just have 1 by 50 crore part of the 100 units passing through it, and that also in around 1,70,000 years. So it's pretty slow energy transfer there. Then you have, after that, the convection zone. We'll talk about it too in details. Now the energy continues to move towards the surface through convection currents, which are the currents here and this layer, and it's kind of a heat transfer here, the convection. So that is the same convection we actually are talking about. That's the convection currents of heated and cooled gas in the convection zone. This actually, where the energy that is transferred is actually made to undergo in the influence of these convection currents. Then we have the photosphere, then comes the chromosphere, and then the corona streamers, which is that the outward flowing plasma of the corona is actually shaped by the magnetic field lines into these tapered forms, and these are known as the coronal streamers. These are the streamers which actually move out into this deep space, even towards the earth sometimes. And these are the solar flares which actually may actually harm us in our future too, by destroying our communications and all, and networks and all. But probably that is quite a rare event, so we don't need to worry too much on that. But these are the coronal streamers, and also about the other things we will discuss. So let's take a look at this. We can take even a screenshot of it. We just discuss about this, and we will discuss even further. So let's move on. Now let's talk about the photosphere. Now, what is the photosphere? The photosphere is actually the outermost layer of the sun from which radiation that is visible and otherwise is emitted. Now, the photosphere, as we know, is actually not very smooth. It consists of small granules. These are the tops of convection cells that carry heat upward from deep within the sun. Now, you can see there is a, in the right side image, there is a mark that I have done. There is a marking of in blue, yellow colored. So you can see this is actually a granule there. Now, this is actually a very zoomed image of the sun's surface. Now, these granules are not very small as they might look from above. These are around this, one of these, if you consider this box to be kind of a rectangular box, then the length of this rectangle would be around 1500 kilometers in length, and the width would be around 900 kilometers or even 1000 kilometers in length. So these are pretty huge um, marks over here. And it's not just marks, these granules are too big because we know that the sun is even like 12,750 kilometers in diameter, and the length we are talking about is around 1000 kilometers. It is just 1/12 of the size of the sun, of the diameter of the sun. So it's too big to actually talk about. So let's talk about what causes the granulation of the photosphere. Now, it's actually, in one word, we can say that the granulation is caused due to convection, which is a kind of heat transfer that happens in this layer. Now, the granulation can be actually visualized as a top layer of a region where due to convection currents, hot gases from the photosphere actually moves upward. As you can see, it actually moves upward. Sorry, it actually moves upward, and then the center of the granule is so hot and so hot that it emits more and more radiation and becomes brighter in magnitude in comparison to the edges of the uh, photosphere. So the edges of this photosphere appear to be quite dimmer, and that's why you have the granulation forming over there, because they are the dimmer regions over there. And also they are not just dimmer, but they also are relatively cooler than the other regions of the sun too. Further, the solar granulation provides observable evidence supporting the idea that exists a convection zone below the photosphere. So it is not just a theory that we say that there is granulation because of the convection, but the granulation that we can see with our observation also proves that there is a convection zone that where this convection currents flow and this convection happens below the photosphere. So this is why we have the granulation there, which is primarily due to the convection. You can see here the granule boundary, the granules here, and this granule boundaries, we say the edges are relatively cooler and dimmer. So let's move on. Now, who doesn't know about sunspots, right? These are something that we all know about. We even discussed a little bit in the previous slides. Now, these are the sunspots that you can see. These are relatively cooler regions of the sun, and these are actually caused by the disturbances in the sun's magnetic field welling up to the photosphere. Now, these are kind of the things that we actually see even from Earth. If you have a good telescope, solar telescope, or from an observatory, or if you just search on the web, you will get millions of pictures of the sunspots too. Now, there are regions, moreover, which are slightly cooler than the surroundings. And by cooler, I don't mean very cool. The overall surface temperature you can assume to be around 5800 Kelvin, where the temperature of these solar sunspots is around 3800 Kelvin. And as we discussed, it's caused by the disturbances of the sun's magnetic field, due to which there are convection currents welling up to the photosphere, and due to these magnetic disturbances, uh, we can see these sunspots. Also, we will see more of it. Like these are the this is the famous butterfly diagram, which actually shows the area of the sunspots versus the latitudes of the sun. Now there is a pattern of these sunspots. It's not like they will always be at the same place and there will be only the same number of sunspots there. It actually increases, decreases. It doesn't remain same. It is also observed that the first sunspot zone appears at latitude of around 35 degrees in say the northern hemisphere or the southern hemisphere, and then it actually migrates to the lower altitudes, the lower latitudes, till it reaches a latitude of around 10 degrees, as you can see in this picture. The EQ means the equatorial region, and these are the 30-degree north, 30-degree south latitudes that you can see. Also in the upper picture, you can see the number of sunspots that have been detected so far from around starting from 1900s, 1910 to around 1985 and still counting. So this is the kind of pattern that you would get. This is a kind of daily motion that if you even trace these sunspots over a period of time, you will see that the number of sunspots will actually eventually be diminished, and also will actually be able to know and observe some new sunspots too if you observe it across a vast time interval. So some highlights so far that we all have seen, we have studied about the sun's surface, about the sun, and so we are ready to actually take in more, right? So let's move on. Now the magnetic behavior of the sun. Now the sunspots, as we have discussed, actually also swap polarities between the north and south hemispheres in every 11 years. It is thus a 22-year cycle, because the north becomes south, the south becomes north, and then it just that the south becomes again south after 22 years. So there is a period of 22 years, right? That is actually like the solar coronas, sorry, the solar sunspots actually you can assume in kind of like some positive and negative charges. If there are positive and negative charges there, then you will have it to be like positive to negative, it will change, and in that sense you will have like the positive and negative becomes the negative and positive after 11 years, and then the negative and positive becomes again positive and negative after another 11 years. So they move around the north and south hemispheres, you can say, and this takes around a period of 22 years cycle. So let's move on from the sunspots. Let's discuss now about the chromosphere. Now, the chromosphere is actually a relatively thin layer of the sun, which is called the chromosphere, and is actually sculpted by the magnetic fields lines that restrains the electrical charge plus solar plasma. Now, this is actually not solid or liquid, as we know. We actually have to know that the surface and these layers are solid plasma, which is another state of matter, you can say, and the density of this layer is around 1 by 10,000 of photosphere, which means it's 10,000 times less dense than the photosphere. It's relatively so less dense, right? So this is about the chromosphere. Now you might actually face a trouble in understanding what is the difference between a chromosphere and a photosphere. So let's discuss that too. But before that, we go into the corona. Now, corona is actually the outermost layer of the sun. We can observe a corona mainly during the eclipse region, because the intensity of this corona compared to the intensity of the photosphere is actually very dim. So in case there is a moon covering in case of eclipses, so the photosphere actually gets hidden behind this, and so we can only see the outer regions, as you can see in the black picture in the right hand side, that the we can see these streams coming out. This is a corona, which is actually a collection of ionized elements within the corona that glow in the X-ray range and the extreme ultraviolet ranges too. From this only we say that there comes the solar wind, and also that is these streams flow out through our entire solar system, through different planets and all. It ranges out and actually flows to entire heavy empty space. So this is what the corona is, and the source of sun's radio emission and for X-ray, the photosphere's black body radiation that you can say, if you take the sun as a black body, is negligible at this wavelength that you can see. So let's move on. Now, as we actually have asked that what is the difference between the two layers, the chromosphere and also the photosphere. Now, the photosphere is actually, you can see that the photosphere actually is the surface, the quick surface over here. But the chromosphere is actually like these jets are coming out, the specules, the jets like this are coming out from the sun's surface. You can see that the chromosphere is actually this part. So if you imagine, I can give you an analogy too. Like if you have a cake there, a cream layered cake, the cream would be the chromosphere, you can see, and the surface of the cake without the cream, just beneath the cream, would be the photosphere. So this is what you can actually remember for not forgetting the difference between the two. The chromosphere is always above the photosphere. This is the chromosphere, and this deep within the surface is the photosphere. So I hope the difference between them is clear. Now let's talk about the temperatures of this gas that we just studied. Now the corona is actually quite hot in temperatures. It's around 1,000,000 degrees Celsius. Whereas the upper chromosphere, like the chromosphere has a thickness of around a few thousand kilometers, and the upper part of it is around 10,000 degrees Celsius, while the lower part is around 4,000 degrees Celsius. And the photosphere, which is the surface of the sun, you can see, is actually around 6,000 degrees Celsius. Now you can see that from the photosphere to the lower chromosphere, the temperature decreases by 2000 degrees Celsius. Now from the lower chromosphere to the upper chromosphere, we can see that the temperature again increases by about 6000 degrees Celsius. But this is all okay, the trend is fine. But the thing is that just after the upper chromosphere, you have the corona, which has a tremendous jump. It jumps from 10,000 degrees Celsius to 10 to around 10 lakh. Like it's 10,000 to 10 lakh. It's 100 times the temperature that you can see, the 1,000,000 degrees Celsius, which is primarily due to the ions that we have there, the ionized elements that we talk about. These are pretty hot there, and these reactions will cause, they actually make it even hotter than these temperatures and make it even hotter and so much lot hotter than the other layers. So you can say, just conclude with that the corona is actually the hottest layer in terms of all of these layers. So let's move on. So let's actually take a look at our solar visits, the space missions we have been planning by NASA or by ISRO, that have been planning or have been executed so far. So let's take a look at them, because it's essential to know about them, because they are the key to understanding the sun in deep. Because if we are very close to the sun, then only is it very much possible that we can actually study the sun in great details. So let's start with some spacecrafts that have been planned and also have been executed. Now, first of it is the Pioneer 6A mission by NASA, and the mission objective was to measure the magnetic field phenomena, the solar flare particles, and the ionization in the interplanetary region. Now, don't get confused with the term interplanetary region. Interplanetary region means the space, um, means the space neighboring to all the planets in the solar system and also neighboring to the sun. It's just a fancy term which actually tells you like interplanetary region, and it actually looks to be around a very fancy term, but it just means that it's a region nearby to the other planets. So that was the job of this spacecraft. Then we also had some famous spacecrafts with the Helios A, Helios B by DFVLR, NASA. Now the full form of this DFVLR I just don't remember, but this is a German organization, and there is have NASA, National Aeronautics and Space Administration. The mission objective is to observe the solar wind, magnetic and electric fields, the cosmic rays, and the cosmic dust between Earth and Sun. Then we have the wind mission by NASA. We have solar wind measurements. Also, we have the ACE mission at last, NASA, by NASA, with also aims at solar wind observations. We also have some Genesis mission, like the solar wind sample return. Now, the tragic thing about this is that this actually collected sample, ionization samples and all samples from the solar wind, but it crash landed on the return to Earth. But still, it's happy to say that actually much of the data has been recovered. So it was not a unsuccessful mission. It was almost a complete 100%, almost a complete 100% successful mission. Now, DSCOBR discovered mission by NASA. We have, it's also aimed at mainly the solar wind and the coronal mass ejection monitoring, as well as the Earth climate monitoring. Now we can actually see that we understand these terms even more deeply, like the coronal mass ejection we just saw now, and the solar winds we also saw, right? So we know what this actually means. Also, we have the Indian mission, Aditya L1 proposed mission by Indian Space Research Organization, ISRO. And actually, this is a solar corona observation mission, which is planned to actually be launched in the mid of 2022. So it's probably the next solar mission you all are going to see. So let's move on and discuss about some of these missions. Now, at the beginning of this presentation, we talked about the heliosphere, which means the sphere that actually engulfs whole of the solar system. It also engulfs the solar system's planets and everything in it. It's kind of a boundary to the solar system, you can say. Now, this is the first mission. This was the first mission of its kind to actually map the heliosphere at the outer reaches of the solar system, where the solar wind that we see interacts with the interstellar space. And this was quite an interesting mission to study about. If you want to study about these, you can just try down the mission IPX and know more about them. Now, we also have a very famous mission, which is the Parker Solar Probe of NASA. This was launched pretty recently in the year 2018, and its mission objective is to make observations of this outer corona of the sun. Now, some further details you can always find out from the NASA websites and all, but the most interesting details you can see is that it will approach to within 9.86 solar radii distance from the center of the sun, which is around 10 solar radii, which means the solar radii is around 696,000 kilometers, right? And so, the 10 times that, it means it's around 7 lakhs or 70 lakh kilometers distance. It's so close to that, right? It's so close to that. It would be reaching so close to that, and then it will reach in the end of it by 2025, and will actually travel at a very high speed of around 690,000 kilometers per hour, which is all we can convert it into this and compare it to the speed of light. It's around 0.064% of the speed of light. It is fastest thing that ever built by humankind till now, and it will reach such speeds at such solar radii distance, at such close proximity to the sun. So it's quite interesting, and even in 2025, so it's quite late from now, but yeah, in future we will be able to see this. Also, we have the Solar Dynamics Observatory (SGO). You can find more about it too. So it's actually designed to help us understand the sun's influence on Earth and the near Earth space by studying the solar atmosphere. And on small scales, space and time in many wavelengths simultaneously, like in many ranges, infrared, UVs, and all the ranges, simultaneously it can actually measure and analyze this data to actually give us the information about it. This was kind of an observatory that was launched, but it was a space mission that was launched. So let's move on from this. So let's finally talk about an aurora. Now, what is an aurora? We know about an aurora. We probably might, most of us might not have seen it with our own eyes, but we all have actually seen what an aurora is. So I'm sure all of you might have just heard about it or have seen also in YouTube videos or in some other places, but it's quite interesting to watch them. An aurora is actually a colorful light show in the sky caused by the sun. The aurora actually happens when particles from the sun interact with the gases in our atmosphere, causing beautiful displays of lights in the sky. It usually happens in the regions of the North Pole and the South Pole. Now, why exactly at the North Pole and South Pole regions? And why not in the other places? Now, we actually know that the Earth has its own magnetic field, right? So the magnetic field, if you imagine to be in terms of magnetic field lines, they stretch out in such a, if you visualize them, they are like this discs and these lines that you can see. This blue lines represents the magnetic field. It stretches out like this. And so the only way the sun's radiation in this yellow colored region, this sun's radiation can enter the earth and not be deflected by these and deflected by these magnetic fields, because these magnetic fields which are wherever there, they don't allow the solar radiation to come to the earth, but the polar regions are not immune from that. The solar radiation actually finds its way through these layers, the sprinkled white colored layer that you can see here. So it actually enters the earth at the north polar regions and the south polar regions. Not exactly the north pole and south pole, but even if you go to some places nearby it, Norway or some Greenland or somewhere, so you can actually see this kind of lights there in the night, and it's quite interesting and terrible to watch because these are pretty amazing scenes which you can actually see, because these are the sun's lights, and these bottommost picture you might always have seen, these are tremendous number of lights, because it doesn't look even of our own world. It appears to be like something animation or something kind of built in, but it's actually real, and this is what causes the auroras. Let's talk a little bit more on these auroras. So what causes the auroras? Now, excited atoms. Now, this causes auroras between 14 and 350 kilometers altitude above the Earth's surface. Now, the incoming electrons from the solar wind that we have, this radiation, the excitation, this incoming electrons from this radiation of the sun, this actually excites the oxygen or nitrogen atoms in the atmosphere. Now, we all know that the Earth's atmosphere is around 78% nitrogen, around 21% oxygen, and some other trace gases too. And so these, you can say almost that these excitation, the incoming electrons will only mostly interact with this oxygen and nitrogen atoms. Also, it will interact with the other atoms too, but majorly it will interact with the oxygen and nitrogen atoms in the atmosphere, and these will excite them. Excitation means that we have like the Bohr's model and the other models that you might have studied till now. So you have these electrons in stable orbits, in Bohr's orbits, and there are some specific energy levels. So if these incoming electrons strike these layers, these oxygen atoms, they interact with them. The electrons may get some excitation and they might go into some other orbit. And this excitation causes the electrons to shift the orbits. And this shifting, you can say, is actually due to an energy difference. This causes an energy difference to be there. And this energy difference actually we perceive with our eyes as color. For different atoms, it would be different in nature as the energy associated with it is actually different. We can also calculate what kind of color, what a particular element will actually give. So for oxygen, the emitted light is actually typically green, whereas for nitrogen, it is actually generally red in color. Now, it is these colors that gives these auroras their distinctive colors, like the green, the red, and the other colors too. Now, we have this atom excitation, we have this atom de-excitation of this, which causes these auroras. So this is what actually causes these auroras to have their distinctive colors. Not only green and red, we also have the other colors here, like the yellow colors also you will find some orange colors, but mainly you will find these colors too, this green and red. So let's conclude this webinar with the references that we have used so far. So you can actually visit these websites and take into account the uh, videos that we have studied here. So these are these you can take a snapshot or something. So actually have the references and study in some more details. So thank you everyone.